Hello, this is Ligaya from Boost Revision and welcome to this live chemistry clinic revision session. In this session, we're going to go over the key details on practical activity 3 from the OCR specification, which is about enthalpy determination. In case you're not on the OCR board, this is also required practical on the AQA specification and a core practical on the EdXL specification. None of the practicals are so specific that the information doesn't transfer between them. So this should be applicable to any of the main exam boards that you might be doing for A-level. So in this live session, I'm going to go through the main things to think about in these practicals: how to carry out enthalpy of neutralisation experiment to determine the enthalpy of neutralisation, and also how to carry out an experiment to determine the enthalpy of combustion. As well as actually looking at the details of how to carry out the experiment, we're going to look at the main sources of error, how to improve those experiments based on the sources of error, and also how to calculate uncertainty or the percentage uncertainty from the different methods that we're looking at and based on the apparatus that you're using. If we have time at the end, we'll go through some example questions of how this might be questioned in the exam. But really today is about focusing on how the experiments are done and how or where issues may arise in the experiment. So in a second, I'm going to share with you my screen so that we can see some diagrams of the experiment itself, looking at how to set it up, and then also how to calculate the enthalpy change from the results in your experiment. So in a previous live a couple of weeks ago, those of you who've got access to all of the live, that should be most of you if you're online here today, a couple of weeks ago I did a live for year 12 on energy. In that we focused in more detail on actually calculating enthalpy changes from values that you get given in your experiments. And we also looked at Hess cycles and calculating bond enthalpies in that. So we may not spend as much time looking at calculating the actual enthalpy changes from this experiment, from these experiments today. We'll be focusing mostly on the practical side of things, how to set things up and how to evaluate your experiments. So as I said, these are the practical activity groups or core practicals, required practicals for the different specifications on screen here. We're going to first start by looking at the enthalpy of neutralisation. So first of all, on the screen here, we've got two different neutralisation reactions. This first one is between hydrochloric acid and sodium hydroxide, making sodium chloride and water. So that's a common neutralisation reaction that most of you will have come across already. It's commonly done in titration reactions. And if we write this into an ionic equation, the purple line simply shows us all of the ions that are in those solutions. So we've got H+, Cl-, Na+, and OH- on the left-hand side, and on the right-hand side we've got the Na+, Cl-, and the H2O water that's made, molecule that's made. If you remember back to how to draw or write ionic equations, in an ionic equation we want to only include the ions that change in either charge or state of matter. So we have both the chloride Cl- and the hydroxide, the sodium Na+ ion on the left and the right hand side. So we can actually cancel out that from both sides, and that's what leaves us with the orange equation. The H+ plus OH- goes to H2O. So it's only the H+ and OH- that actually change in their charge or state of matter, because they're changing from the ions separately into a molecule of water, which is no longer able to be separated because it's now a molecule in liquid form. So the same thing is true for actually any neutralisation reaction, which is why I've shown you the example here of the sulfuric acid reaction at the bottom. So in the sulfuric acid reaction, we are also reacting it with sodium hydroxide, and then it's making sodium sulfate and water. And here, because the sodium hydroxide, here because the sulfuric acid contains 2 H+ ions for every molecule of sulfuric acid, then we've got 2 H+ ions in the as the ions floating around the solution, and we have to balance it with 2 Na, 2 OH, etc. And so we have the different balancing that you see on the purple line there. Again, we want to, in order to draw the ionic equation, we want to identify which of these ions are changing or not from the left-hand side to the right-hand side. And again, hopefully you can identify that the sulfate ion is the same on both sides. The 2 NAs also cancel out from each other. And then we're left with 2 H+, 2 OH-, and 2 H2O. And because we have the 2 on either side, the 2's also cancel out, which leaves us with the same ionic equation for this neutralization reaction. So even though we have a different acid that balances differently in its chemical equation, we actually end up with the same ionic equation. And this is true of any acid and alkali neutralization reaction. And so this is why when we're calculating the enthalpy of neutralization, the definition of it is the enthalpy change from the formation of 1 mole of water, I'm going to highlight that, in a neutralization reaction. So any neutralization is going to involve the exact same ionic equation. That's supposed to make a square, sorry about that. It's going to involve this exact same ionic equation. Okay, that's happened again. Shouldn't have happened. Anyway, H+ plus OH- makes H2O, which is our neutralization reaction for any neutralization reaction you can come across. And therefore the enthalpy change of neutralization is always going to be looking at the formation of 1 mole of water. If you're comparing an experimental value for enthalpy of neutralization with a theoretical value, i.e. something that you're reading out of a data booklet or a chart that you've been given, where you're usually being given the standard enthalpy change of neutralization. And just remember that this symbol means standard conditions. And while there may be various reasons why your experimental value may differ from the data book value, which we're going to look at later on in sources of error, remember if your data book value is specifically a standard enthalpy change, then one of the reasons why your experimental value may differ is if your experimental setup hasn't involved standard conditions, which you may remember is 25 degrees centigrade, or 298 Kelvin. So the temperature, that's the standard temperature. Pressure is 1 atmosphere, or approximately 100 kilopascals. And if we're talking about anything that involves solutions, we also need 1 mole per dm cubed of your solutions in order for it to be under standard conditions. So that might be relevant in an enthalpy of neutralization reaction where we've got 2 solutions reacting with each other to form a salt and water. So just remember standard conditions there. Okay, so how do we actually do the experiment to measure the enthalpy change of neutralization? Well, usually you have a simple reaction vessel that could be a beaker, but in this case is usually something like a polystyrene cup. And there are some more and more complex pieces of equipment that you can use to measure this really, really accurately. But usually in your school lab, you'd be using something like a polystyrene cup. You put your reaction mixture into the polystyrene cup and then make sure you place the thermometer into the reaction mixture so that you can measure the temperature change as the reaction progresses. So why might we use a polystyrene cup instead of a beaker? And that's because we're measuring an enthalpy change in a reaction, so the change in energy. We want to know if energy is given out or taken in, and if energy is given out, let's say we want to know how much is given out. So we want to make sure that the equipment that we use is going to capture all of that enthalpy change. And so we want to use whatever apparatus we have that is going to be the most insulating. So the reason that we use polystyrene instead of a glass beaker, let's say, is because this is a relatively insulating or insulated material. Sometimes you might even find you might double up your polystyrene cup to give an extra layer of insulation. Other things, and we're going to talk about this more in a second, thinking about sources of error. Other things you may also see as your equipment setup is you might see a lid being put on top of this situation, on top of this polystyrene cup. And that's going to prevent any heat that might be lost in the top of the cup, so up, up through here. So insulating our reaction mixture by using insulating material like polystyrene and adding a lid to minimize any energy flow or airflow between the reaction inside and outside of the vessel are going to help to make sure that this experiment is going to be as accurate as possible, i.e. measuring, capturing all of the enthalpy change that we're seeing. In terms of if you were asked to describe how to do this experiment, you would usually be expected to describe how much of your acid and alkali you're putting into your reaction mixture. This is in a neutralisation reaction. So we're going to obviously put some acid and alkali. Usually if we're using something on this kind of a scale, like a beaker scale, we're usually using about 50 centimetres cubed of each of these things. And we would also usually want to make sure we know the concentration of the acid and alkali. And remembering back to what we were talking about, standard conditions, we might usually want these to be at 1 mole per decimeter cubed of concentration, so that we can compare our values that we get from our experimental result to some standard tables, for example. So you might want to know the concentration or set the concentration at 1 mole per decimeter cubed. When you're setting it up, you would normally put one of those two things in the beaker initially, get everything else set up, pour the second solution into the beaker, replace the lid, and then measure the temperature rise or decrease. Of course, you'd want to measure the start temperature at the beginning before you add the second solution, and then wait until the temperature stops changing at the end to know that your reaction is complete and that all of your reactants have finished reacting. So from your thermometer, you're going to measure a start temperature and an end temperature, and that will obviously eventually give you your temperature change. Now, you may or may not already know, but neutralisation is normally a slightly exothermic reaction. So we would expect a slight increase in temperature that would end up giving us a slightly negative value for our enthalpy change of neutralisation. And that's just something that might be useful to know in case you're trying to check whether your results are what you would expect to see. So this is the basic setup. We need to have a thermometer to measure the start and end temperature. That will give us our overall temperature change. We want to know how much of the reaction mixture we put into the reaction, and obviously for a neutralisation reaction, that's going to tell us how much acid and how much alkali we have. That will allow us to know how many moles of water are being formed, and therefore we will later on be able to work out our enthalpy change per mole of water, which is our enthalpy change of neutralisation. So we'll go into the more details of the calculation in a couple of slides, but first I just want to talk a little bit more about sources of errors and improvement. We've already talked a little bit about that in looking at the setup of the reaction, but it's just worth knowing that there are several different places that you could have a source of error in your experiment. The main source of error, however, is going to be heat or energy loss. As we talked about earlier, in this case, we've tried to minimize the amount of energy or heat lost by insulating the equipment using polystyrene. A completely separate source of error would be non-standard conditions, as we were talking about. If we were comparing our experimental value to data book values for standard enthalpy change of neutralizations, then if we had non-standard conditions, perhaps slightly warmer temperature than room temperature or 25 degrees centigrade, or perhaps colder temperature, then we may not get the exact value that we would expect. Potentially, you might also have heat or energy absorbed by the beaker or apparatus that you're using. And then there could also be some measurement error based on the precision of the equipment that you're using, perhaps like a measuring cylinder versus a pipette. So when we're talking about ways to improve your method, you want to consider the different sources of error, which ones of those you may have control over in terms of changing the apparatus that you use perhaps, and to make it more precise or more insulated, that kind of thing, and which ones perhaps you don't have control over. Remember, there's also two main types of error. There's random error, which you don't really have much control over, but that's one of the reasons why we would repeat an experiment several times. That way, if we've got some errors that are randomly slightly higher and some measurements that's randomly slightly lower, then over several repeats they should cancel each other out, which is why we normally take a mean. Repeating the experiment as a potential improvement for your experimental method is also useful because you can then identify anomalous values, so values that are perhaps something you wouldn't expect. Maybe someone just forgot to measure the temperature on time and they left it for too long, which meant that the temperature was way lower or way higher than you would have expected it to be. So we normally want to repeat experiments in order to minimize random error. And the other type of error is systematic error. And that's normally a bit harder to fix, but systematic error means that you're going to have the same error reproduced every time due to something about the way you've set up your equipment. So again, these are the things that we can try to minimize by using the right type of equipment, doing things to minimize heat loss, doing things to minimize measurement error, etc. Okay, so when we're talking about sources of error, in the exam and sort of analysing your experiment, you may be expected to calculate uncertainty values. And there's a standard equation for this, which is percentage error equals the uncertainty of your equipment. And I'm just going to write there, here we go, equipment. And that's usually given as something like plus or minus 0.1 centimeters cubed or something like that. And then you've got your uncertainty divided by your measurement or reading. So this is, let's say if we're measuring 50 centimeters cubed of your acid, then that's going to be your, well, I'll just say e.g. 50 centimeters cubed. And then times it by 100, obviously, to give you your percentage. So percentage error is the uncertainty from your equipment divided by the measurement that you took with that equipment times by 100 to give you the percentage. The thing that's slightly tricky here, and that's what I've written down here in this, this starred area. Remember that if, my boxes are really not working today. Okay, so remember that if you're taking two readings, for example, you're measuring a temperature change, which is what you're doing in this enthalpy change reaction, then you have to double your uncertainty value, the one that's on the top of the reaction, of the equation there, because you have to measure a start temperature and an end temperature. So you're taking two readings and your uncertainty is going to apply to both of those readings. So for a temperature change, we would have to do the uncertainty times 2 divided by the temperature change that you calculated, so the start minus the end or the end minus the start. So in this context, it's temperature change we'd be talking about, but in other contexts you also want to keep that in mind. So anytime you're measuring a change in mass or a change in volume. If you're measuring something at the start and then at the end again, you have to keep in mind that you're going to use that piece of equipment twice, and therefore your uncertainty has to be doubled. But that's only, like I said, if you're actually taking more than one reading. The other situation in which this might happen is if you perhaps want to measure a large volume, let's say 100 centimeters cubed, and you only have a small measuring cylinder available, let's say 25 centimeters cubed. So then, even if you're measuring one volume, like 100 centimeters cubed, if you've only got a small measuring cylinder, you're going to have to use that measuring cylinder 4 times to measure your total volume. And therefore, each time you use that measuring cylinder, you're adding that amount of uncertainty. So the measurement value, which is on the bottom of your equation, will stay the same, but your uncertainty is going to change depending on how many times you use that piece of apparatus to measure what you were trying to measure. So we're going to do look at an example question here, just to put that into context and think about how that actually works in the context of a question you might get asked. So we'll skip that first question for a second because I haven't given you any details of the exact experiment that's taking place. But this is effectively an enthalpy change reaction where the main error in the procedure would be heat loss. And therefore, the main way that a student might modify the apparatus to reduce this error would be insulation of some kind. But let's focus on this calculation of uncertainty. So the student evaluated the measurements in her experiment. The student used 100 centimeters cubed measuring cylinder to measure the 50 centimeters cubed of hydrochloric acid that was in the experiment. This measurement volume had a maximum error of plus or minus 1 centimeter cubed. The thermometer that she used had a maximum error of 0.5 centimeters cubed for each measurement of temperature. Okay, so part 1 asks you to calculate the percentage error in the volume of hydrochloric acid measured in the experiment. Okay, so the information has told us, okay, we've got percentage error, we want the uncertainty, which was here, the 1 centimeters cubed. So 1 plus or minus 1, and then we measured 50, that was here. So 1 divided by 50 times by 100 should give us our percentage error. 1 divided by 50 times by 100, and that is 2. So I get 2 for that. So our percentage error here is 2. We're using the uncertainty value for the measuring cylinder and the measurement that we took, which was 50 centimeters cubed. In the next part of the experiment, part of the question, we want to calculate the percentage error in the temperature rise of 5 degrees obtained by the student. So we just have to be careful here and think about what we talked about with measuring a temperature change. So the percentage error here will be 2 times 0.5, which was the error of our thermometer from the question, divided by 5, which was our overall temperature change. So 2 times 0.5 divided by 5, and that gives us, times by 100, okay, and that gives us 20%. Okay, so we can see here that for 2 reasons, we've got a higher percentage error in our temperature rise value than our volume percentage error. One reason is that the precision of our measuring cylinder was more appropriate to the measurement that we were taking. So the 1 centimeter cubed was a much smaller proportion of the 50 centimeters cubed that we were measuring. And this gave us a smaller percentage error. So in general, again, another thing you can think about for improvements is making sure that the equipment that you're using is the appropriate size for what you're measuring. So if you compare the volume, which is 1 to 50, to the temperature change, even though the thermometer at 0.5 degrees centigrade looks like it's perhaps more accurate than the measuring cylinder at 1 centimeters cubed maximum error. Because we're only using that to measure a temperature rise of 5 degrees, that 0.5 is a much bigger proportion of what we're measuring. So ideally, in an ideal world, we would want a much more accurate thermometer, or we want to measure a much larger temperature change, and that would help us to minimize the percentage error. So whenever we might be talking about ways to improve our experiment in terms of minimizing the error from measurement of our values, the best way to do this if you're designing your own experiment is to choose a large enough amount to measure that will give you a good ratio between your percentage error and the measurement that you're taking. The second reason why we've got a larger error in the temperature change is because, as we saw in the experiment, in the calculation, we needed to times the error by 2 because we were using that piece of apparatus twice to measure our temperature change. So that's going to have actually had twice the effect on that small value of 5 degrees centigrade that we were trying to measure. So hopefully that makes a bit of sense. I know some people do get quite confused with calculating uncertainty, why we sometimes have to times it by 2, why we sometimes don't. So it's all about how many times you're using that piece of apparatus to measure a measurement in your experiment. Okay. So finally, the last thing we're going to look at on this enthalpy of neutralisation is how to actually calculate your enthalpy change of neutralisation from the information you get in your experiment. So hopefully you'll have seen this before. If not, go back to a couple of weeks ago. I think it was near the end of March when we did the revision session on energy, and we went over this in more detail there. But there are 2 main equations that you need to do to calculate your enthalpy of neutralisation from your experiment. The first one is Q equals MC delta T. The thing to be careful here is what the MC and delta T are referring to in your equation. So Q is going to basically stands for the energy change in your reaction. So this doesn't matter how many moles or anything you used. This will be to do with what you actually use in your reaction. So earlier we put 50 centimeters cubed of acid and alkali. So this is going to measure what the energy change is in joules for that reaction that we did. And because we're measuring this enthalpy change of neutralisation, remember that we have all of this in a solution in a polystyrene cup or a beaker. The temperature change that we measured was the temperature change of the solution or of the reaction mixture. Therefore, our mass and our mass and C, which is specific heat capacity, needs to also relate to that solution. You need to be given the specific heat capacity, but that's you're normally assuming that your solution is going to have the same specific heat capacity as water. So this C is specific heat capacity, usually of water. And the thing where people often go wrong is this mass. So M stands for mass. And in this case, we want the mass of the solution. Or if we're talking about the temperature change and assuming that it's the same as for water, we're talking about the mass of water. So now if we put 50 centimeters cubed of acid and 50 centimeters cubed of alkali in, then our solution is the 50 plus the 50 to give us 100 centimeters cubed. And you may or may not be told in the question that you can assume the density of water or the density of solution is the same as the density of water. That's important because the density of water is 1 gram per centimeter cubed. That means for every gram of water, it takes up 1 centimeter cubed of volume, or for every 1 centimeter cubed of water, it weighs a mass of 1 gram. So even though the value that we want to put into the equation is mass, we actually use the equivalent of the volume of the solution to say that that's equivalent to the mass, because the density of water is 1 gram per centimetre cubed. So the mass is going to be 100 grams because the volume of the solution was 100 centimetres cubed. The specific heat capacity of water, as I said, will be usually given to you either in the question or in the data booklet, and that's approximately 4.18, or sometimes you just round up to 4.2. And then your temperature change is obviously what you measured in your experiment. So let's say, for argument's sake, it's going to be 5 degrees centigrade. So then you put all of these pieces of information into your calculation, and that gives you your value for Q. One thing to just remember there as well is just when I highlighted here that the value there is in joules, and that's important because of the next stage where we want to calculate the enthalpy change, which is in kilojoules per mole. Okay, so stage 2 is to work out how many moles of water we've produced in our neutralisation reaction. So this is thinking back to the definition of enthalpy of neutralisation, which is the enthalpy change associated with the formation of 1 mole of water. So we need to know, well, how many moles of water did we have in step 1 in order to divide that total energy change by the number of moles of water that was formed, and that will give us our enthalpy change per mole of water that was formed. So it's important to be able to work out from your neutralisation reaction, which remember was H plus OH minus goes to H2O, how many moles of water we were formed. So for example, if we had our 50 centimetres cubed, let me move this out of the way for a second. Okay, I'll change the colour for a sec. So if we have 50 centimetres cubed, let's say, of 1 mole per decimetre cubed HCl, then we can work out how many moles we have of our HCl. Moles equals volume times concentration. So we would do volume, which is 50 divided by 1,000, because we had 50 centimetres cubed, we have to convert to decimeters cubed, times by the concentration, which was 1. So that gives us 0.050 moles, or 0.05 moles. If we had that many moles of hydrochloric acid, we can do the same thing for the alkali, the sodium hydroxide, if that's what we were using. Obviously, all of this depends on what the actual solutions you are using in the experiment are. And you also have to be careful of whether one is in excess or not. We want to be looking at the number of moles of water that are produced. So if we had 0.05 moles, that was supposed to be an underline. If we had 0.05 moles of our acid, that's going to refer to this. We're going to assume, for the sake of this demonstration, that we also have 0.05 moles of our alkali, and therefore we also have 0.05 moles of our water. So from the information you get given about your volumes and concentrations of your solutions, you should be able to work out how many moles of your acid alkali you have, which one is in excess, therefore which one is limiting, and you use the limiting reactant moles to work out how much water is going to be produced. Because obviously if you're looking at the one which is in excess, you're going to have some left over, so you're not going to use all of that. You want to focus on the moles of the limiting reactant. That will tell you your moles of water, and ultimately, to calculate the enthalpy change of neutralization, we want the moles of water. So use the information from the experiment and your balanced equation to work out how many moles of water you had. So now we have a value for Q, which we got from step 1, and you have a value for your moles, and you can put that into step 3 to work out your delta H. So the only thing to remember here is that Q, step 1, was in joules, And step 3, delta H, is in kilojoules per mole. So you need to divide your Q by 1,000 in order to make sure that you've got the correct relationship between your units. So if you divide Q by 1,000, that turns joules into kilojoules, and then you've got kilojoules per, this is your moles here, per mole. Or obviously you could just do your calculation minus Q divided by N, and then divide the answer by 1,000 at the end to take it from joules per mole into kilojoules per mole. So that's just something to keep in mind. You might ask me, well, why do we have this minus here? And that is just simply to do with what we learned about at the beginning of learning about energy changes, exothermic and endothermic reactions, is that Q was talking about the energy change effectively of the surroundings of the reaction. So the energy change that we saw in the water or in the solution. But delta H is talking about the energy change that we see in the chemicals. So what we remember from the basics of enthalpy is that if a reaction is releasing energy, then that reaction is exothermic. It's going to have a negative delta H, and the energy released is going to be absorbed by the environment, in this case, the water. And that's going to, if it's absorbed by the environment, that's going to produce an increase in temperature in the surroundings, which in this case is the water. So an increase in temperature, a positive Q, will give you a negative delta H. And so that's why we just have to change the sign effectively of the Q to get the right delta H. So if our temperature change was positive, we'll have a positive Q. And by changing the sign of that, it gives us a negative delta H. If our temperature change was negative, our reaction cools down. That means we had an endothermic reaction. So again, we have to take that negative value for Q and turn it into a positive value for our delta H. So that's just to make sure that we're differentiating between the temperature change we measured, which was the surroundings, and the enthalpy change we're trying to calculate, which was in the chemicals, in this case, the acid and the alkali, rather than the actual water in the solution surrounding it. So as I said, we went through some examples of how to actually put this into practice a couple of weeks ago in the energy revision session. So if you want more practice on that, then please do go back to that session. The replay is all available on the website. If we have time, I'll do an example of it at the end, but before we finish off the session, I want to go through the differences between calculating enthalpy change of neutralisation or a reaction of solutions like we've just done, and calculating enthalpy change of combustion, which is another key type of reaction that you might come across in determining enthalpy change experimentally. So the enthalpy change of combustion, as a definition, is the enthalpy change from the complete combustion of 1 mole of a fuel. And I've said in brackets excess oxygen because theoretically complete combustion and excess oxygen actually mean the same thing. We want to be combusting a fuel in excess oxygen. If there's excess oxygen, that means the fuel will completely combust and therefore will have a complete combustion. That's important because later on we might again be talking about sources of error and how to improve the experiment. And one of the potential sources of error is if you perhaps may have incomplete combustion instead of complete combustion in your reaction. So here are just 2 examples of reactions that involve a combustion reaction, or reactions that we might see in an experiment that we might want to use to calculate the enthalpy of combustion. And the key thing here is, as I highlighted earlier, that we want to be making sure we're measuring the enthalpy change of combustion of just 1 mole of our fuel. So in this case, we've got our fuel there on the left-hand side reacting with our excess oxygen. And depending, I've given the second example there to show that, some of you, if you were asked to balance that second equation, you might have ended up putting perhaps a 2 here, a 13 there, 8 and 10, but that would give us 2 moles of our fuel, and we want to only have 1 mole of our fuel, which is why I've shown the difference there of showing the different ways of balancing the equation, which however we balance the equation, we must always make sure that we have just 1 mole of the fuel that we're actually combusting. And that's why I've given those 2 examples. So you could have any fuel here. Usually the ones we're looking at are hydrocarbons or organic compounds like alcohols, which give us carbon dioxide and water when they combust fully in oxygen. But it is possible and it is conceivable in exams that you may be presented with a different type of fuel that perhaps doesn't just produce carbon dioxide and hydrogen, maybe has sulfur in it or something like that. Maybe it has nitrogen in it, but the most common fuels produce carbon dioxide and water. So just get used to balancing these equations, making sure that we've got just 1 mole of fuel. Again, similarly to what we did earlier with the enthalpy change of neutralisation, just remember that if you are going to be comparing these values that you measure experimentally to databook values, you would usually be comparing them to standard values, and therefore you want to make sure that your experiment is done as close to standard conditions as possible, 25 degrees centigrade and 1 atmosphere of pressure. For combustion reactions, we don't normally have to think about the concentration of solutions because we're not doing a reaction involving solutions. So this is more or less what our apparatus will look like. Our liquid fuel will be in a spirit burner that is normally going to be closed with a cap, and then you would remove in order to light the fuel. In order to actually get all of the information you need to be able to calculate the enthalpy change, we need to know the mass of the fuel. And therefore we want to calculate or measure the mass that you had at the beginning before you lit the wick. So start mass, and then the mass that we had at the end. So after the fuel has burnt for, let's say, 5 minutes, we're going to have less fuel remaining at the end. And so the difference between the start mass and the end mass will give us the mass of the fuel that was burned, mass of fuel burned. The reason we need to know the mass of the fuel burned is because that will give us the moles of the fuel that we had. Mass over MR will give us the moles of the fuel that we burnt, and we need that in order to work out our enthalpy change per mole. So when we're describing how to do the experiment, you're going to talk about having your liquid fuel in a spirit burner, and you measure the mass at the beginning with the lid on usually, and then do the experiment and measure the mass again at the end, again with the lid on, to make sure that you're comparing like to like. Then, as you can see at the top section here, we're going to use the burning of that fuel to heat up some water that will be contained, usually in a beaker made of copper. It's usually made of copper rather than something like glass, for example, because copper is a very good conductor of heat, much better than glass. And so we want to be able to make the assumption that all of the energy released from burning the fuel is going to be absorbed by the water. And so the better conducting material we use for our beaker, the more likely that our energy is going to be transferred from the fuel into the water. Now, of course, this is never going to be perfect, and that's going to be one of the sources of error we talk about and discuss. But that's why we use normally a copper beaker. So again, we want to also know for the purposes of calculating our enthalpy change, we want to know how much water we have here. And normally we would use something like 100 centimeters cubed. And again, that's because this part of the reaction is going to go into our Q equals MC delta T reaction calculation. So we're going to get the delta T, which is our temperature change from obviously the thermometer that's in the water. So measuring the temperature change in the water, we've got our volume and therefore our mass, 100 grams of water. And then we need the specific heat capacity of water, which is 4.18. So the top part of that is, I sort of like to think about it as separate in top and bottom. The top part of that gives us our Q value, and then we want to put our Q value into delta H equals minus Q over N. So the moles of the fuel is our N, and obviously we take the minus Q from the first part of the equation. So one of the most common places that students make mistake here is to either use the mass of the fuel over here, which is incorrect. So that would not be correct. Or to use the mass of the water when calculating the moles of the fuel, or incorrectly calculating the moles of water, which won't actually give you the correct moles. We want to know how much of the fuel burnt in terms of moles, because we want to know how much energy was released per 1 mole of the fuel that combusted. We talked about sources of error in the last equation, in the last experiment. So similar sorts of sources of error we have here. In order for this experiment to be perfect, we want to have standard conditions, and we want to be able to assume that all of the energy released by the flame that's burning the fuel is absorbed by the water whose temperature we're measuring. But we may have heat lost to the air around here, which we could probably improve by putting some kind of insulating barrier like a windshield. We may have heat absorbed by the beaker that obviously wouldn't be measured by the thermometer. And so that could be a source of error. We could have some water evaporating off the top of this solution, which would mean that the temperature change that we're measuring will end up being the temperature change of less water than we would expect. And potentially we might heat this up so much that we actually end up boiling some of the water off. And in that case, we need to consider that some of the heat energy from the fuel might have gone towards breaking the bonds that vaporize the water to make it boil. So that's another thing to potentially consider. So the main source of error, as usual with all of these enthalpy change experiments, is heat loss, but depending on exactly how the experiment is done and whether it's a combustion experiment or a neutralization or a solution related experiment, you may have other things, for example, like the evaporation of water to think about. This point up here says we could also think about the evaporation of fuel. So you may know these fuels are quite volatile, most of them. Perhaps, you know, at the end of your experiment, you stopped the flame, you put out the flame, and you left it for a little while before you actually measured the end mass change, also the end amount of mass. And in that time, perhaps if you forgot to put the lid on, some of your fuel might have evaporated, and that would give you a measurement of your end mass that is lower than what you would expect it to be. So it would look like you used more fuel to burn than you actually did. So if you had some fuel evaporating, you'd have that issue. Another thing to think about for this specifically is that you could have had incomplete combustion, in which case your experimental value is not going to match the data book value, because the data book value is talking about complete combustion. In this case, if you had some soot collecting on the bottom of the beaker or not enough oxygen being able to access that, that fuel, you might have incomplete combustion, which is likely to give you a lower energy change. We mentioned the heat being absorbed by the beaker, and we talked about measurement error before in terms of things like what measuring cylinder you're using to measure the water, how precise your thermometer might be, how precise the mass balance you're using to calculate the mass of your fuel might be. At least with measurement error, you can usually calculate the percentage error in order to actually determine what that error might be. Whereas with something like heat loss, it's a bit harder to work out how much that would have affected your experiment. Okay. So I think we kind of actually went through most of this idea of calculating enthalpy change of combustion, just remembering what I said on the first section, that the Q part of your calculation comes from the water, which is the top half of the the apparatus, and the delta H part, i.e. the moles that you want to be calculating, is from the moles of the fuel. So that's the thing to just really keep in mind. This Q is talking about the water being heated. And then this moles of fuel, this is going to be for the fuel that you actually burnt. So this comes from the change in mass of the fuel that you burnt. Okay, so we already have talked a little bit about specific improvements relating to the main sources of error that you get from these types of enthalpy change experiments. But in general, we want to just consider, when we're evaluating our experiment or considering improvements to our experiment, and we want to think about these three main things. Validity, which is to do with what you might think of more easily as, is it a fair test? Validity is to do with whether your method is actually giving you valid results, which means comparable results. And the main way to make sure you're doing this is to make sure that you've got control variables, or variables that you're controlling, i.e. they're not changing. You're only changing the variable perhaps that you want to be changing. So if you've got some experiment that's hypothesizing, does changing concentration affect the enthalpy of neutralisation? So for example, you could try different concentrations of acids or alkalis. Then you want to make sure that the only thing you're changing is the concentration, and everything else is staying exactly the same. The volume of water, the mass of whatever it is you're measuring, the approximate temperature change, etc. One thing I forgot to mention actually that you might need to include in a description of how to do this combustion reaction is you usually want to set the amount of time you're going to heat up the water for. And that's not normally going to be too long. And that's just something, again, that's going to help you with the validity of your results, to make sure, let's say we only heated it up for 5 minutes each time, and that would give us a good comparable measurement of hopefully comparable temperature changes each time. Other things to think about is if you're repeating the experiment, you want to use fresh water each time, and perhaps a fresh beaker, making sure that the starting temperature will be similar than each time that you repeat it. So you don't want to obviously do the experiment once, heat it from 20 to 30 degrees, then do it again, heat it from 30 to 40 degrees, etc. So you always want to be making sure that you're controlling your variables as much as possible, starting at similar temperatures, such as standard conditions, things like that. Right. So we've talked about validity. The second thing is accuracy. So accuracy is something that's sometimes hard to establish whether your experiment is really accurate or not. Accuracy, the meaning of it is how close to the true value you've got. So there are ways to try and improve your accuracy, but it's not always easy to actually work out if your experiment was completely accurate. But ways to improve that are using the appropriate apparatus. I think what we talked about earlier, if you're measuring 100 centimeters cubed, it would probably be best to use a 100 centimeters cubed beaker. If you're, measuring cylinder. You don't want to use, for example, a 200 centimeter cube measuring cylinder to measure 50 centimeters cubed, because that's sort of a lot of excess, and you're likely, that larger piece of apparatus is likely to have larger error for measuring a smaller amount. So you'd want to use a smaller measuring cylinder to measure that 50 centimeters cubed if you can. Similarly, if you were going to measure 100 centimeters cubed, you don't want to use a 10 centimeter cubed measuring cylinder, because then you'd have to use that measuring cylinder 10 times to get to your 100, and that's going to multiply the error from your measuring cylinder 10 times. So using appropriate scale apparatus, and also using the maximum sensitivity or precision of equipment. So that's the most decimal places that you have on a digital piece of equipment, or the smallest amount of error that you can have on equipment. And then the last thing is reliability. So reliability, the way you can prove that is by repeating the experiment multiple times, taking a mean, and excluding any anomalies, which are any values that don't seem to match the other values, i.e. something went wrong that was unexpected. And all of these three things together minimize both the systematic and the random errors that you might find in your experiments. Okay, so that's the end of what I had prepared for today. I don't think there's really enough time to go through some the details of some questions. As I said, we went through the calculation questions a couple of weeks ago in the energy revision session, and there are some questions on the website for you to download to have a go at, and I'll put the mark schemes alongside there as well so that you can have a go and mark them yourself. Okay, my other camera seems to have died. Luckily, we managed to get to the end of what I'd planned for you to do today anyway. Let me know if you've got any questions by emailing us at chemistry@boostrevision.com or finding us on Instagram and sending us a DM there. We're always happy to help and answer your questions on there. So like I said, have a look at the downloads that are on the website above the video. You can have a go at the questions yourself, look at the mark scheme to check your answers, and feel free to ask us questions anytime. Please also remember to join us on Sunday. Dr. Owusu will be going through Practical Activity 5, which is on synthesizing organic liquids. So that'll be a good one to join as well. And then keep an eye out on the website for future sessions. We're probably going to be doing a mixture of theory from the AS/A2 kind of going on to the start of A2 course, and then also some practical sessions. So hopefully by the end of summer we'll have been able to go through most of the required practicals or core practicals, practical activities for you. So thanks again very much for joining, and hopefully see you again next time.